Good afternoon, welcome back. So today is lecture 37, and in the last class I had begun a discussion of finite fields, and I had mentioned, so let me just quickly take you through the lecture. I had begun by actually saying that we would actually follow two different paths. First, we will actually show how you can construct finite fields, and then after that we will deduce that in fact what is actually true is that the structure of a finite field, of the finite field that we do construct, is in fact typical of the general class of finite fields. And I motivated my construction for finite fields by making an analogy with the class of complex numbers, but I will skip that and just say that so we will provide a construction for finite fields of size q equals p to the power of m for every prime p and every integer m. And then when m is equal to 1, if you take the integers modulo p, then we know that that already forms a finite field. So the interest is in the case when m is greater than or equal to 2. It turns out that finite fields only exist when the size of the finite field is a power of a prime. Okay, so there is no loss of generality in restricting to this situation. So we focus on the case m is greater than or equal to 2, and the way we do it is we take a monic irreducible polynomial. So what does monic mean? Monic simply means that the highest degree coefficient is actually equal to 1. Irreducible means that it cannot be factored into the product of two polynomials, each of who has degree less than the degree of the original polynomial. For example, when p is 2, then this is a list of the irreducible polynomials of small degrees, degree 1, 2, 3 and 4. It can be shown that for every prime p and every integer m greater than or equal to 1, irreducible polynomials of degree equal to m exist. Okay, so we know that such polynomials exist. Then we consider the following construct, that is, we consider the set of all polynomials over the integers modulo p, and we go modulo f of x, where f of x is irreducible of degree equal to m. And at the end of the last class I told you that if you go modulo f of x, then this is a collection of equivalence classes where we define G1 equivalent to G2 if f divides their difference. So this is where we will pick up the discussion. So just a quick recap. We talked about so I can say that we first began by motivating a construction for finite fields, and then the construction itself involved taking f p of x and going modulo f of x, where the degree of f of x was equal to m. So this is our construction. And so first of all, a clarification, that is, you should regard f p x mod f of x. So this is a collection of equivalence classes, where we define g1 of x to be equivalent to g2 of x if f of x divides g1 of x minus g2 of x. So, I will leave it as an exercise, and I gave this last time. Verify that this is an equivalence what that means is that you have to verify that the reflexive, the symmetry and the transitive properties actually hold. Once you verified that, then we are ready for a theorem. Let P be prime and f of x be monic irreducible of degree m over Fp. So, when you say that a polynomial is over Fp, what you mean is that the coefficients of the polynomial lie in Fp. And then now we set R, we define R to be Fp of x divided by f of x, modulo f of x. So, we know that this is a collection of equivalence classes. Okay. So, perhaps I should actually note here. So, we will make a note here. So, we will denote the equivalence class of g1 of x by g1, and sometimes perhaps out of sheer laziness or perhaps because it is not required, we will simply write this as g1 when the x is understood. Okay. So, this notation here indicates an entire equivalence class. So, now with respect to that notation, then under the operations a of x plus b of x is equal to a of x plus b of x and a of x times b of x is a of x times b of x. Then under these operations, if you consider R plus dot is a field. Now, when a mathematician, first of all let me just try to explain this. What this is saying is that, look, you define an addition operation between two equivalence classes by taking a representative from each of the equivalence classes and defining the sum of the equivalence classes to be the sum of the representatives. Similarly, if you want to multiply two equivalence classes, you take a representative from each of the equivalence classes, multiply them and pass on to the equivalence class of their product, and then define this to be the equivalence class of the equivalence class, that is the product of these two. Now, the moment you hear that, you say, well, you know what, since a given equivalence class can have several representatives, how do you know that if I pick a different representative for the same equivalence class, I won't get a different answer? So, that in mathematical language is what people say is you need to show that these operations are well defined. Okay. So, can show, and I think I am a little conscious now, beginning to get a little conscious of the fact that our time is limited. So, I am going to skip all the non-essential proofs, so that I can spend a little bit more time on the codes that this is leading up to. Okay. So, proof, first of all, can show that these operations are well defined. In other words, i.e., the end product of the two operations described above does not depend upon choice of the particular representative. Okay. Now, once we have gotten that out of the way, the question is this does this give us, does this really give us a field? So, the first step is, so step 1, we will prove this in steps. So, step 1, we will show that if you take R plus is an abelian group. Now, to show that something is an abelian group, you need to verify the corresponding axioms. So, you have to check that the axioms of closure, of associativity, of the presence of the identity element, the presence of the inverse, and the commutative axiom all hold. And in other words, what you have to show is that, so for example, if you were worried about closure, you just need to actually show. So, all of this is with respect to the following operation. So, A of x, the equivalence class of A plus the equivalence class of B is the equivalence class of A of x plus B of x. Now, clearly this is well defined, because given any two representatives, we can construct the sum of these as polynomials. So, that's closure is fine, and associativity, if you take 3 of these terms, it does not matter in which order you add them. So, that is also clear. So, some of these are quite obvious and I will not spend time on them. The identity element, if you spend a little bit of time thinking about it, you will see that the identity element in this case is the equivalence class of 0. Now, remember that the equivalence class of 0 is all those polynomials which have the property that their difference is divisible by f of x. So, this is precisely the set of all multiples of f of x. So that is your identity element. So that is also rather straightforward. The inverse, well, the inverse of the equivalence class of a of x is nothing but the equivalence class of minus of a of x. Why? Because simply because if you add these two, you will actually get the identity element, which is this equivalence class. Okay, so now even that has been verified, and commutativity, of course, because simply because the addition in here, the order does not matter, it is not going to matter here. So we verified all of these properties. So that shows that R plus is an abelian group. Next we come to step 2. We need to show that under the multiplicative operation that R satisfies the following. One is, it satisfies closure, the associative property, the presence of the identity element, once again the presence of the inverse, and the commutative property. So once again you have 5 properties to check, and closure is immediate. Now this time we are talking about the operation which says that the equivalence class of A times the equivalence class of B is the equivalence class of A of x times B of x. Okay. So this is what we are actually saying, and closure is immediate just from the definition, nothing to prove. Associativity is just as easily verified in the multiplicative case. The identity element, so the identity element, it is easy to see that the identity element is the equivalence class of 1. So even that is straightforward. Commutativity is also straightforward. So the only thing that really requires some work is the inverse. How do you actually get the inverse? And if you think about it, that up to now we have not used the fact that this equivalence class was defined with respect to an irreducible polynomial f of x. So when we see, we said that this set is nothing but a collection of equivalence classes where we define these two polynomials to be equivalent if f of x divides their difference. And now for the first time we are actually going to use the property that f of x is irreducible. So it plays a role in ensuring that every element has an inverse. So how do you prove that? So we will actually do an example to show how one would compute the inverse in general. Okay. We will demonstrate through example the presence of a multiplicative inverse. So in this example, let us take p is equal to 2 and let us define f x to be x4 plus x plus 1. This was one of the polynomials that was on our list of irreducible polynomials. So there is no problem picking this particular one up, and let us say that we are interested in, let us pick a particular equivalence class, let us say the equivalence class of x plus 1 and ask the question, what is the inverse of this? Now, the inverse of this means that we are actually looking for an equivalence class b of x such that a of x, b of x, which of course is ax bx, is equivalent to 1. That means that we are looking for a second polynomial b of x such that when you multiply a of x times b of x, then the difference between that polynomial and 1 is divisible by f of x. So, here what we do is we call upon the extended Euclidean algorithm, which we discussed some time back. We make use of the extended Euclidean division algorithm. So, we will abbreviate this by EDA, and again I will illustrate through an example. So, what we do is we form, perhaps I will do it on the next page to make sure I do not run out of space. So, we will actually put x4 plus x plus 1 and x plus 1 in two separate columns, and then put x4 plus x plus 1 and x plus 1 on two different rows. Thereafter, what we do is we start a process of dividing. Now, first of all, x4 plus x plus 1, we treat this like an Excel spreadsheet, and so we actually put down this is equal to 1 times this plus 0 times this. X plus 1 is 0 times x4 plus x plus 1 plus 1 times x plus 1. So, I will actually put 1 here. Now, next what I am going to do is I am going to introduce a third column here, which I will write as the quotient. So, what this quotient does is that it divides, you divide this polynomial here by this polynomial. So, you are going to divide x4 plus x plus 1 by x plus 1, and it may be a good idea to do this division on the side. So, you have x4 plus x plus 1 divided by x plus 1, you get x cubed, x4 plus x cubed, you get x cubed plus x plus 1 plus x squared, x cubed plus x squared plus x plus 1 plus x squared plus x, and you get 1. So, what that tells you is that when you did this division, you obtained a quotient which is x cubed plus x squared plus x, and a remainder which is 1. So, we will make a note of that here. So, the quotient is x squared, or rather x cubed plus x squared plus x, and the remainder was 1. Okay. So, this is the remainder, and this is your quotient. Now, so the way we want to fill in these two entries here, and the way you fill it in is like an Excel spreadsheet providing you a formula. So, for example, here the way you got the 1 over here was taking this term here and subtracting this times this. So, the same thing here, you take 1 minus 0 times this, which is 1, and here you take 0 minus 1 times this. Now, since you are working in modulo 2 arithmetic, minus 1 and plus 1 are the same. So, whether you multiply this into this and add, whether you multiply this and then subtract or add makes no difference. So, for that reason what you will pick up here is nothing but x cubed plus x squared plus x. So, in this way what we have actually shown is that So this equation is the equation that's important for us. It tells you that I am able to write 1 here. I am able to write the term 1 here as something times x 4 plus x plus 1 plus something times x cube plus x squared plus x into x plus 1. Okay. So therefore, 1 is equal to x 4 plus x plus 1 into 1 into x 4 plus x plus 1 plus x plus 1 into x cubed plus x squared plus x. So therefore, this is telling us therefore that the equivalence class of 1 is equal to the equivalence class of x plus 1 times x cubed plus x squared plus 1, which is telling us that the equivalence class of x plus 1 times the equivalence class of x cubed plus x squared plus x is equal to 1. Okay. But now you look at this equation, this is the equivalence class whose inverse you wanted to find, and this is it right here, because when you multiply the two you get the identity. Okay. And hence the inverse of the equivalence class of this is the equivalence class of x cubed plus x squared. Okay. Now, okay, so we have found it in this case, but now where exactly did I use the fact that this polynomial f of x here, so this was our f of x, where exactly did we use the fact that f of x was irreducible? Well, if you recall our early discussions on the greatest common divisor, what we are picking up here in this process is the greatest common divisor of the two polynomials at the top here. So we go through all of this, and then what you are going to do is, if you did proceed one step further, what you would actually get is a 0 here. So the greatest common divisor is just the entry above 0. I think I mentioned that earlier. So this is the greatest common divisor. But since f of x is irreducible, unless this polynomial is a multiple of f of x, which in our application it will not be, the greatest common divisor is going to be 1. So you are going to end up at some point in this calculation with a 1 on this side, and that means that something times f of x plus something times x plus 1 will give you 1. In this way you are always guaranteed to find an inverse. Hence, in this way we are always guaranteed to find an inverse. Okay. So hence is a field. Now I want to actually point out a simplification, and I will do this by example. So just like, so let's go back to our discussion in the last lecture where we were talking about real and complex numbers. So we said that it's actually possible to think of the complex numbers as being obtained, take the real numbers, take polynomials over the real numbers, go modulo x squared plus 1, and then you will recover the complex numbers. And the complex numbers we think of in terms of the imaginary element I, but that I is nothing but I is played the role of I is played by x over here. So rather than work in polynomials, equivalence classes of polynomials, people find it easier to just say, that is really very cumbersome, maybe isn't there an easier way out, and in fact there is, because instead of going modulo x squared plus 1, because modulo x squared plus 1 means please feel free to discard any multiple of x squared plus 1. Instead of that, we bring in a fictitious element I having the property that I squared plus 1 equal to 0. Okay. And the moment we do that, this assumption, this fictitious element, because this is equal to 0, it takes care of the requirement that we discard multiples of x squared plus 1. So therefore, instead of thinking of this collection as a set of all polynomials of the form a plus bx, and where you do multiplication modulo this, you just work with a plus ib. Okay, so you just bring in this fictitious element I, and then that means that you no longer, and as provided you keep in mind the fact that I squared plus 1 is 0, you no longer have to actually keep carrying around this modulo sign. So in the same way, now in lecture 37, we know that this is a field, but it's cumbersome to keep thinking of it like this. So what we'll do, and I'll illustrate this in so an example of our construction of the construction of a finite field of size equal to 16 as well as of its representation in terms of an imaginary element alpha. So here p is equal to 2, m is equal to 4, f of x is x4 plus x plus 1. So that means that strictly speaking, one should consider fp of x modulo f of x, or in other words, you should consider the set of all binary polynomials modulo x4 plus x plus 1. So which means that all your elements would look like polynomials. Now a word about this. This is saying that since you are free to discard multiples of x4 plus x plus 1, that means that you can actually replace x4 by x plus 1. Okay. So what we will do is, instead of working in terms of the x's, we introduce the imaginary element alpha, which is a 0 of x4 plus x plus 1. So what we mean is that alpha 4 plus alpha plus 1 equal to 0. So we assume that that will be our starting point. Now then what happens is that because we assume this to hold, then f2 of x modulo x4 plus x plus 1 will be precisely the set of all polynomials in alpha. Okay. So what does the finite field end up looking like? So we can start, because alpha satisfies a polynomial of degree 4, every element in the finite field can be represented as a polynomial of degree 3 or less. So, this tells us that f2 of alpha, which is our finite field, is the set of all polynomials of the form ai alpha to the I goes from 0 to 3, where ai is either 0 or 1. And you clearly, since the coefficients are allowed binary choice, there are 16 such elements. Now, so that would say that our finite field looks like, now you consider every possible set of these coefficients and you will find out that there are, you can think of them as 4 tuples. But here is something interesting. Supposing instead I do not do this, but instead, for reasons that will become clear later, what I do is I start computing powers of alpha, because even this polynomial representation of the finite field is in a sense not the simplest representation possible, because supposing you want to walk away with a mental image of a finite field, then thinking of them as polynomials turns out to be more complicated than it need be, and we will see that in just a second. So, instead of working with polynomials, let me start by taking powers of alpha. So, I start with, of course, let us start with the 0 element, and then we will take alpha to the 0, which is 1, alpha to the 1, which is alpha, alpha to the 2, which is alpha squared, alpha cubed, which is alpha cubed. Okay. So, sounds like we are not doing anything up to this point, but now when it comes to alpha to the 4, this is all of a sudden alpha plus 1, reason being because alpha 4 plus alpha plus 1 is equal to 0. So, alpha 4 is alpha plus 1. Then we go to alpha 5 is equal to alpha squared plus alpha, alpha 6 is alpha cubed plus alpha squared, alpha 7 is alpha 4 plus alpha cubed. But since alpha cubed is alpha plus 1, this is equal to alpha cubed plus alpha plus 1, alpha 8 is alpha 4 plus alpha squared plus alpha, which is alpha squared plus 1. Okay, you can verify that because alpha to the 4 plus alpha is 1, so it is alpha squared plus 1. Okay. Okay. Then alpha to the 9 is alpha cubed plus alpha, alpha to the 10 is alpha 4 plus alpha squared, which is alpha squared plus alpha plus 1, alpha to the 11 is alpha cubed plus alpha squared plus alpha, alpha to the 12 is alpha 4 plus alpha cubed plus alpha squared, which is alpha cubed plus alpha squared plus alpha plus 1. Alpha to the 13 is alpha 4 plus alpha cubed plus alpha squared plus alpha, which is alpha cubed plus alpha squared plus 1. Alpha to the 14 is alpha 4 plus alpha cubed plus alpha, which is alpha cubed plus 1. Okay. And now you have your let us go one more step and then I will say what I was going to say. So, this is alpha 4 plus alpha, which is alpha plus 1, which is 1. Okay, what is this? This looks most mystifying. What exactly were we trying to do? Now, what I was trying to do is saying that, okay, we started out by saying the finite field looks like this, and we said we do not really like this. So, we will replace x by alpha and assume that alpha satisfies this equation. So, this is very much like saying I squared plus 1 is equal to 0 in the case of the real and the complex numbers. So, we just assume and we keep this at the back of our minds that it satisfies this, then it is very easy to see that every element in the finite field, because it is a polynomial in alpha, and whenever you get up to degree 4 you can fold back using this expression, using the fact that this is 0, that means alpha to the 4 is alpha plus 1. So, any time you get up to degree 4 you can bring down the degree again. So, that means that you never have to go up to degree greater than 3, and on the other hand it is clear that every such element belongs to the finite field. So, the finite field then contains of these 16 elements. But next what I said is that wait a minute, even that is not the most convenient representation of a finite field, because let us take a look. So, this is like magic, okay, at least it is magic if you are looking at it for the first time. So, this is 0, okay. So, we are not there is the 0 is a rather special element, okay, all the other elements are non-zero. So, we put 0 aside and then start working on the non-zero elements. We begin with alpha to the 0, which is 1, and then alpha, alpha squared, and we keep multiplying. And we notice that as we keep multiplying, you keep every time you keep getting a new polynomial of degree 3, of degree 3 or less. You always end up with a degree 3 or less polynomial. You can check, and the number of such polynomials is 16, and every one of them is going to appear here. And you can check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So, there should have been 16 polynomials of degree 3 or less, and every one of them has appeared here. For example, you might say, well, what about alpha cubed plus alpha squared plus 1? Okay, so, let us look for it. We look for it, and then sure enough we see that alpha cubed plus alpha squared plus 1 is here. Any polynomial of degree 3 or less is to be found here. Okay. But at the same time, that we see from this table is only one representation of the elements in the finite field. There is another surprising representation, and that is in terms of the powers of alpha ranging from alpha to the 0 to alpha to the 14. This alpha to the 15 we have to ignore, because after all this is a duplication of a previous element. By the way, there are 2 elements in here. Yeah, so this is a duplication of a previous element, so we do not count that as a different element. So, the conclusion is that right now it is just an interesting phenomenon, but later on we will see that this is actually part of the structure of finite fields, that every finite field has this beautifully simple structure. Okay. From the table, we observe that the finite field also has representation in terms of the element 0 and the various powers alpha. So, that means that your F, the finite field of 2 to the 4 elements, can be represented in the form 0 union alpha to the I, where I ranges between 0 and 14. And the interesting and very useful point about all this is that every finite field has such a representation. So, in fact, a finite field can be represented, every finite field can be represented in these 2 ways. That is, one is where all the elements are represented in terms of polynomials in this imaginary element alpha, and on the other hand they can also be represented as powers of an imaginary element alpha. Now, this imaginary element alpha, you have to exercise a little bit of care in choosing it, but not too much, and it is not difficult. All right. So, that is so now I have given you a construction for finite fields, and hopefully now you know how to construct a finite field of any size of the form p to the m for any prime p and any integer m greater than or equal to 1. Now what we want to do is, remember I told you that we are going to take two different approaches towards finite fields, and the first is the constructive approach. So, we have just completed the constructive approach. Now, we are actually going to take on the deductive approach. We are going to put on a different hat and say, okay, supposing I am in an armchair and I am just relaxed and I am saying, okay, I know that I have a finite field and I know that it has to satisfy certain axioms. What can I deduce just from the knowledge that it is a finite field? Okay. So, that is what we will try to do next. So, I call this the deductive approach to finite fields. So, all that we do, our starting point is here, let Fq be a finite field of size q, where q greater than or equal to 2 is an integer. All right. Now, we know that the finite field, since it is a finite field, we know that there are two operations, plus and this, and we know that associated to each of these operations you have an identity element. So, under plus there is an identity element which we will take to be 0, and under multiplication there is an identity element which we will take to be 1. Okay. Because right now we are looking at an abstract object and all that we know about it is that it is a finite field, but we know because it must satisfy the axioms of a finite field that there must be an additive identity and there must be a multiplicative identity. So, in terms of notation we are going to denote the multiplicative identity by 1 and the additive identity by 0. All right. Now, let us say, well, if this finite field contains 1, so Fq, we know that it contains 1, therefore, it contains 1, 1 plus 1, 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1 and so on. Now, let us, when we will write this as 3, 3 means 1 plus 1 plus 1, that is what we mean in the finite field. Now, since the field is finite, this list keeps going on and on and on and on forever. So, it must be that there must be some repetition in this. Okay. So, this list must repeat entries, which means that all the entries in this list cannot be distinct. Therefore, m is equal to n for some n greater than m. It must be that. Now, what do I mean by m? M simply means m 1 plus 1 plus 1 plus 1 m times. That is what we mean when we say m. And similarly, when I say n, what I really mean is 1 plus 1 plus 1 plus 1 n times. Okay. But if this is true, but this implies that n minus m is equal to 0. Why do I say that? Well, what I really mean is that, look, here you are adding n ones. So, think of n as 7 and m as 5. Here you are adding 7 ones and here you are adding 5 ones. So the difference between the two is 2 ones. So if 5 ones is equal to 7 ones, then I can cancel 5 of the ones by adding -1 5 times to the left and to the right, and I am left with the fact that 2 ones is equal to 0, or 2 is equal to 0. Okay. So that means that n minus m is equal to 0. So let, and you can think of this as n minus 1 times 1 is equal to 0. Let p be the smallest integer such that p times 1 is equal to 0. Then p must be prime. Why? Because else, if not, p is p1, p2, implies that p1, p2 is equal to 0 in the finite field, but that forces p1 equal to 0 or p2 equal to 0. Okay, so because every integer which is not a prime can be factored into the product of two integers, each of which is less than p. Okay. So for example, if you add 6, if p was 6, let us say, you could say that 3 times 2 was equal to 0, but then either 3 ones had to add to 0 or 2 ones had to add to 0. Okay. So that means either, so that is a contradiction, because we assume that p was the smallest integer with this property. So this contradicts the minimality of p, hence p is prime. Okay, so we have found out the first, we have deduced the first fact about our finite field. The interesting fact that in any finite field of whatever size q, there is some prime number such that if you add the identity element to itself a prime number of times, you get 0. Okay. And we will just say that p is 0. So this prime number is called the characteristic of the finite field. This prime number is called the characteristic of the finite field. All right. But if you think about it, so here you have your big finite field, and then inside it you have sitting these integers 0, 1, 2 up to p minus 1. Okay. What do I mean by that? Well, by 2 I mean 1 plus 1, and by p minus 1 I mean 1 plus 1 plus 1 p minus 1 times. Now, however, p is 0. So within this set, the way I add and subtract is according to modulo p arithmetic. Okay. So in this set, so in the finite field, within this set, one carries out arithmetic modulo a prime p. What that means is that if you think about it, that this is really nothing but the finite field of signs p, which is the integers mod p. So that means, because for all purposes you can pretend that you are working with the integers modulo p. Why is that? Because the same rules apply in the integers modulo p as well as in this set here. P is 0, you treat p as 0 here as well, and you are adding just integers here, you are adding integers there. So that means now what you do is you identify this subset with the integers modulo p, and then what you have is an interesting situation when you have a larger finite field fq containing a smaller finite field fp. Okay. So that is the point at which we will stop today. So today what we did is that we completed our construction of the finite fields. So now you have with you a method of constructing any finite field of size p to the m for any prime p and any integer m. The only ingredient that you need is the irreducible polynomial of degree m over fp, but that can be found through textbooks. Okay. So now you know how to construct a finite field of size p to the m. Then we said, okay, let us now go back to our deductive approach and see what can we deduce about a finite field just from the knowledge that the field is finite. And we have already seen that the finite field must then contain a prime number, a very special prime number called the characteristic, and that it contains a smaller field whose size is equal to the characteristic. And we will pick up the discussion from here in the next class. Okay. So with that I will leave you. Thank you.